Welcome everyone. In this first lecture, we will introduce the notion of groups. So, here we have the question, what are groups? Most of the textbooks introduces groups using mathematical formulation. So, in my opinion, the mathematical formulation comes at the end after seeing examples. So, we try to introduce groups via examples. So, you may be surprised to see groups are there everywhere. For instance, they naturally arise from number theory, geometry, combinatorics and more. So, there are branches of mathematics dedicated studying some particular groups like Lie groups, algebraic groups, Coxeter groups, etc. We will see some examples which are more accessible for time being. So, later I will try to explain some non-trivial groups coming from higher mathematics. So, let us be very practical. So, I want to introduce this group that is actually coming from all possible moves that we can apply on Rubik's cube. So, all of you must have seen what is this Rubik's cube. Okay. So, it is also called magic cube. It is actually consisting of one 3D puzzle. So, it was invented by a Hungarian sculptor and professor of architecture E. Rubik in 1974. So, let us see how groups are naturally appearing in solving Rubik's cube puzzle. So, let us fix one Rubik's cube, call it capital C, and consider all possible allowed moves that we can perform on it. So, we can actually, for example, rotate horizontally 90 degree, 180 degree and so on, and similarly we can also rotate vertically 90 degree, 180 degree and so on. But it can happen that two moves might result as the same configuration of the cube. So, in that case we will consider the moves are same. For example, rotating a face clockwise by 180 degree is the same as rotating the same face counterclockwise by 180 degree. For example, look at this cube. So, what I mean by that? So, you take this particular position. Okay. So, if I actually rotate this cube 180 degree horizontally, let us take this last cubes and then just rotate it 180 degree. You see that this red cube is actually in this position. And similarly, if you go back to the original position and then rotate 180 degree in the counterclockwise, then you can see that this is again, this position is again red. So, that means the configuration is not changing using these two different moves. So, in that case what we say that those moves are same, okay, because after all we are only interested in what configuration that we get at the end. Okay. So, note that after this identification each move changes the configuration of the cube capital C except the empty move. So, for example, you can start with this ideal position of the cube. So, in which you can see in this slide, okay, so where all these cubes are in the original position, where the reds are all in the one side, greens are all on the other side and yellows are all there. So, this is actually kind of ideal position of the cube. Okay. So, this is where we want to actually kind of converge. So, you start with some configuration, finally, you want to bring your Rubik's cube to this ideal configuration. But let us go back, let us start with this ideal configuration, okay. Then you start applying the moves. So, then we will arrive at some random configuration of the cube, okay. But who guarantees you that by performing again some moves that are permittable on this cube, you can go back to this ideal configuration or the original configuration of the cube. Okay. So, this is where actually you can see the group theory is hidden. Okay. So, in In some sense, you can see that for each moves that you perform on the Rubik's cube, you have what is called the inverse move. Okay. So, if you start with this ideal configuration and then start performing many random moves and then you reach some move like this. So, then by reversing, so you may not remember of course, but if you start writing down the moves that you have actually performed on the cube and then reversing those moves step by step, you will be able to actually reach back to the original this ideal configuration of the cube. Okay. So, let us explain this much more using the group theory. Okay. Of course, one will be interested in solving the cube first of all. So, that means one wants to actually guarantee that by starting with any random configuration something like this, by performing the possible allowed moves, you will be able to actually go back to the ideal configuration or the original configuration that is shown in this picture. So, why that is always possible? That is first question, and the second question is there any better way of solving? That means, is there any fast way of solving? So, algorithmically speaking, can you actually produce some algorithm so that you can solve this Rubik's cube very fast? Okay. So, I believe you must have seen many videos in YouTube that actually teaches you the algorithms, but if you think about it, so those are all actually those algorithms are arrived based on group theory. Okay. So, those things I will explain in this course later. So, when we develop enough tools in group theory, using group theory language, I will actually explain how to solve Rubik's cube. But anyway, let us now focus on all possible moves that we can apply on the Rubik's cube. Of course, modulo the identification that I already told, because two different moves can actually give us same configuration of the cube. So, in that case we identify those moves as same moves. Okay. So, now you see, if we start with two moves, say M1 and M2. So, then we can apply first M1 and then M2 and get a new mu. Okay. So, this new mu is just obtained by first applying M1 and then M2. So, it makes sense to call this new move as M1 M2. So, it is some move, okay, whatever it is, I can just simply call it M1 M2. So, this is the level of abstraction that one is interested in, and then that is what allows us to actually study these moves in one go. So, that is all about group theory. So, instead of studying each move individually, all we want to do is we actually collectively want to study all the moves that we can perform on the Rubik's cube. Okay. So, now look at this property. So, this is called closure property. You actually started with two moves and then you are able to actually associate some new move related to those given two moves M1 and M2. Okay. Now, let us take three moves, what we can do. So, call them M1, M2 and M3. So, note that it does not matter if we apply M1, M2 first. So, M1, M2 is a new move, okay, that actually we already defined what it is, and you apply that first and then you apply M3 secondly. Okay. So, then you are going to get some new move by applying this order. Okay. You apply first M1, M2 and then you apply M3. So, now we can also do the other thing. Okay. We can apply M1 first and then M2, M3 second. Okay. So, again we are going to get another move, okay. But it is not hard to see, at the end you apply these two different moves on the Rubik's cube, we are still going to get the same configuration of the cube. Okay. So, because we are going to get the same configuration of the cube, we can say that these two different way of applying these moves on the Rubik cubes are same. Okay. So, more precisely using mathematical formulation, we can say that, so the bracket M1 M2 times M3. So, this is the new mu, okay. It is obtained by first applying M1 M2 and then M3. Then the second new mu, which is called M1 times M2 M3, where you apply M1 first and then M2 M3 second. So, we say these two are same, okay, and this mathematical property is called associativity. Let us move on. What is the advantage of associativity? Okay. So, we want to only keep track of the order in which we apply the moves, not the grouping. Okay. So, that is where the associativity is useful. Okay. For example, so here all matters is you apply M1, then M2 and then M3, and then it does not matter whether you first apply M1 M2 and then M3 or M1 first and then M2 M3. So, only the order matters, not the grouping. So, I will leave it as exercise. Now, using the associativity, you can prove by induction that given any list of moves, call it M1, M2 etc. MR, even though there are many ways to apply these moves by grouping them. So, with the same ordering, so the ordering should not be changed, but you can group them in many ways. Okay. So, after that you will be getting some configuration on the cube, but each grouping you may expect it may give you some configuration on the cube, but using associativity you can convince yourself that the resulting moves, okay, so they all actually give you same configuration on the cube. Okay. So, that is why the resulting move actually you can call it just M1 times etc. MR without actually introducing these brackets. Okay. So, let us look at one example. Let us take R equal to 4. So, then I have given you two examples. Okay. Of course, there are many ways to group them. So, in this you can see that, so you are first applying M1, then M2, then M3, M4. So, this is the brackets that tells you, so how you are applying the moves on the Rubik's cube. But then later you see you can also do something like this, first you apply M1, M2 and then apply M3, M4. Okay. But what we are interested in? We are interested in what will happen at the end. So, how the configuration changes, but you can see that by applying these two different types of moves, okay, still the configuration will be same. So, because we are only interested in the end result, that is the configuration of the cube. So, because of that we can say that these two moves are same, okay, that is our actually identification. So, okay, so this is the advantage of associativity. So, now we have one weird or some unique way of applying a move. Okay. So, what is that? That is called empty move. So, basically we do nothing to the cube. So, that is still permittable move. Okay. So, you take that particular move, then you see that, okay, so you apply that move, call it E, and then you apply some other move M, then it just amounts to saying that you are just applying M. Similarly, you apply M and then you apply E, then again it amounts to saying you are just applying M. Okay. So, there is this unique move called empty move. So, that plays this role of identity element. So, E M equal to M E equal to M. And most important property of group elements, that is the existence of inverse. Okay. So, that is what guarantees that Rubik's cube puzzles have solutions. Okay. So, I can start with this type of very random configuration of the cube, but even though it is very random, okay, this configuration is obtained by applying successive moves from the ideal configuration. So, which is shown here in the picture. Okay. You start with this ideal configuration of the Rubik's cube, you start applying all the permittable moves, okay, then you end up like this. But each move that you apply, okay, for example, you can rotate vertically 90 degree. So, that has the inverse move, okay. You can do the same thing, you can reverse it, okay. You can do the other side, you can just rotate again 90 degree, then you will be getting the inverse of this move, okay. Similarly, if I want to rotate here like this 90 degree, then again I can rotate back. Even if I rotate 180 degree, again I can rotate back 180 degree. So, this tells us that each move that you are performing on the Rubik's cube, that has inverse. Okay. So, that means any given move M1, we have some move called M2 such that M1 M2 is identity. So, what I mean by identity, that means you are going back to the configuration that you started with. So, if I rotate 90 degree like this and then rotate back to 90 degree, then you have gone back to the configuration that you started with. So, that means you haven't really done anything to the configuration. So, it just stayed as it is. So, that is what empty move does. So, then I can say that M1 M2 really actually does what empty move does. Okay. So, since each move has its inverse and this random configuration is obtained by applying finite number of moves on the ideal position of the Rubik's cube. So, by reversing them, what you can do, you can go back to this ideal position that is shown in this picture. Okay. So, that is why Rubik's cube puzzles have always solution. Okay. Now, this is also somewhat motivates you to actually see what are all possible moves that we can apply and then like how it really affects the configuration, and by studying them, okay, basically what we call, so we have actually defined this group, okay, which is just a set of all permittable moves that you perform on the Rubik's cube, okay, and then you actually identified them if they actually gives you same configuration of the cube, and then you defined what is called binary operation on that set, okay, which is we called it that M1 M2, you apply first M1 then M2, and then that binary operation we just proved it actually satisfies these laws, what is called associativity and then existence of identity and then existence of inverse. So, that set of all moves modulo the identification that we define using this binary operation, it is what actually forms a group. So, indeed if you think about it, we are actually talking about this group which is there underlying. So, we are talking about the group action on this Rubik's cube. Okay. When I actually tell you, so this is what we have to actually kind of understand very well in mathematics. Okay. This is called abstraction or mathematical formalization. So, we are not interested in the configuration of the cube, okay, or we are interested in only the how the configuration actually changes. So, these moves how we actually applied on the Rubik's cube, that is what we are interested in. Okay. So, instead of taking all this set of all configuration, okay, so which we may be interested in studying, but instead of taking those configuration, indeed what we took actually, we actually took what are all the possible moves that we can apply on this Rubik's cube. Okay. So, indeed the configuration changing is actually tells you how the group is actually acting on this Rubik's cube. Okay. But what is the underlying group? The group is set of all permittable moves with the identification that we told. Okay. So, this is something very important. So, we have to actually we should not get confused with the group and the group action that actually it is acting on the set. So, we will see more examples later and I will explain more how again groups are naturally appearing from elementary number theory, geometry and combinatorics. Okay. So, by seeing many examples, so we will see that groups actually indeed studies the symmetries of the object in which it acts. Okay. So, I will actually introduce more examples in coming classes. So, I will stop now. So, I hope you must have got some idea about what is group from this lecture. So, I will continue in the next lecture with the more examples. Thank you.